an acid. Shout it out whenever you're good. Go for it, Emily. What? Hydrochloric acid. Okay. Hydrochloric acid. It acts as an acid, right? It is an acid. What do Bronsted acids do? They donate. They donate what? Protons or H pluses or hydrogens, however you want to say it. Same thing. Make this donate an H plus. What does it become? Just chloride, right? Because it has donated its only H plus out into the world. So this is an acid, and this is its conjugate base. That's called a conjugate acid-base pair. Give me a base. Let's go. Let me give you one. Ammonia. What is ammonia? NH3. NH4 is ammonium, right? So ammonia with an IA at the end is just NH3. So I will tell you, ammonia acts as a base. What do bases do? What do conjugate acid bases do? What do Bronsted bases do? They accept a hydrogen, so make it accept a hydrogen. Okay, sorry, a hydrogen 1 plus, because there's a proton, right? So NH4 plus 1, right? So this is the base, and this is its conjugate acid after it has achieved an additional H plus. So that should give you some insight on what this I think it was 15 that asked for the conjugate bases, right? What did 15 give you? It said write the conjugate bases of who? Phosphoric acid. Okay, so phosphoric acid, first off, make it act as an acid 1 time to lose 1 H. Make it lose 1 H. Okay, so when it loses an H, sorry, it is an H plus, by the way. When it loses an H plus, it becomes H2 because it lost one of the H's, PO4, and it was neutral over here, meaning no charge. Right here, it should be what? Say again? -1 because it lost up one of its pluses. That means it drops down to a negative charge. Okay, so this is the acid. This is one of its conjugate bases. Well, then this still has additional H's, true? Can't it lose some more H's? So it can lose, and that's why I said bases, because it specifically didn't want more. Make it lose another H. H. PO4, so now we're down to 1 H, went from 2 to 1. Charge. 2 minus, because it lost an additional positive charge, so it goes doubly negative. Okay, so that's another conjugate base, and then there's one more, because you can see it still has one more H remaining. What would that last one be? PO4, 3 minus, and who's that? That's phosphate, so that makes sense that after 3 deprotonations, or 3 losses of H's, it now becomes just plain old phosphate. So there are 3 conjugate bases because there were 3 different H's. What do you call an acid that has 3 H's? Say again? Triprotic. Good. That combination is ever there. Thank you. All right, let's do one more, a couple more that are related to kind of more multiple choice based questions you should be familiar with. This one's not multiple choice, my bad. Oops. So, describe a chemical reaction in which between an acid and a metal. So write down any chemical reaction between an acid and a metal. So come up with your own example. And think about what kind of reaction it is. Kyle, give me an acid.
Acetic acid.
Acetic acid. Thank you for thinking outside of the box. HC2, H3O2. Give me a metal, Rishi. Zinc. Okay. What kind of reaction does this have to be based on the 5 types that we know, guys? Raise your hand when you know. Maybe somebody from that area over there that no one has their hands up for. Go for it, Jillian. It has to be a single replacement. We have a single guy, his name is Zinc. He has the ability to displace something here, but don't forget acetic or is acetate, that needs to stay together as happy family. Zinc has the ability to form a positive ion because it's a metal. This is the only thing over here that has a positive charge, so these have to switch places, right? What does that make? Robbie, tell me one product.
Hydrogen gas.
Hydrogen gas, good, because he said H can't be booted out by itself. It has to be a mini-me, right? So it's got to be hydrogen gas, H2. And what else? How do you write zinc acetate? Uh-huh. Anybody else? 2, because zinc has a 2 charge. Remember, Z looks like a 2. That's the one you have to memorize. Okay. Then this be balanced by this. There we go. All right. So last 2 questions. You guys take a minute and determine which below is an acid based on the characteristics. Give me a thumbs up when you're ready. Nick, tell me individually, like go W, X, Y, and Z, and tell me yay, nay, and why or why not.
W is not.
Because?
It turns lid.
And that's indication of a base, right? Okay.
Yeah.
What else? Or what's what? X?
For X, basically X and Y into paper fluid.
Okay. There's a couple more on here too. So these are both indicative of a base. And what about this? This is indicative of a base. Bases are bitter, like soap in your mouth. Not so great. That's a base. Feels slippery. Soap feels slippery. That's a base. Okay, so all of those are like characteristics of bases for sure. And then tell me about Z.
It turns paper red and it's sour.
Right, so those are 2 pretty easy characteristics of acid you should know. Okay, and then lastly, this is more about ion concentrations. Which of the following would be known as an acid based on the concentrations given to you here? Give me a thumbs up when you're ready. And these are exponents. Just it didn't come out that way on the smart board, like to the -8 to the -6.
Teacher, pardon the interruption. Please dismiss the students with last names beginning A through D to the auditorium for the assembly for the 10th graders, the current 10th graders to the assembly in the auditorium at this time. Also, teacher, please set your recycling bins outside the door. Thank you.
All right, that's only a couple of you guys. Drop your problem sets in the box before you leave. I will answer it and I'll get it back to you. I'll answer on video.
You want the
Labs in the box too. Yep. Bernice, Caroline, Person, Leo. Your labs and your problem sets in the box, please. All right, thanks guys. Watch the video. All right, so raise your hand if you're ready for number 4. Go ahead, Julian. Tell me what you think. Give me the explanation that goes along with that. -8, yeah.
So I think E would be the acid because anything with more than 10 to -7 concentration of a rate of hydroxide ions would be basic.
And since this is less
That's the
than
only
that.
one that doesn't have that amount. So.
Right, so these right here, these all fall above 10 to the -7th molar. 10 to the -7th is right at the splitting point that makes something acidic or basic, because if you have equal amounts of hydroxide and hydronium, that means actually they all have 10 to the -7th, 1 times 10 to the -7th as their concentration. This would be pH neutral, so pH of 7. So if you have less or greater, then you are acidic and basic. Thanks, guys. Have a good time. So this is definitely lesser amount of base, so it must have more acids. Can anybody tell me, based on the fact that the exponents, when they're 1 times 10 to the blank, the exponents have to equal 10 to the -14th? What would the hydronium be if the hydroxide is 10 to the -8? Rishi? 10 to the -6. Good. So basically, oops, not 16, 6. Gosh. So this together, 10 to the -6 plus 10 to the -8. What's 6 plus 8? I mean, sorry, -6 plus -8. -14. And that's what the concentrations of these together, when you multiply them, isn't this one your pH formulas? So this is 10 to the -8, and this is 10 to the -6. that's 10 to the negative 14. So those do add up together in your log kind of ideas. So who feels like they've got about 50% of those page formulas memorized because you use them so much now? Okay, you guys have to keep referencing your notes. You need to memorize those. Okay, that's something that you guys will have a 8 question quiz on, not just on pH formulas, not only that, but definitions of acids and bases, the categories that you guys have in your book, properties, looking in your little booklet, determining a conjugate. So if I give you something, you determine the conjugate based on how does it act, like if it acts as an acid. If it deprotonates or loses an H+, if it acts as a base, it's gaining one or accepting one, and then some pH calculations. But there's only 7 or 8 questions on this, so you can only imagine there's probably 1 or 2 of the pH calculations on there, okay? So do practice that. We're going to practice them a bit more today, so I think you'll kind of get those ingrained in your brain. So, number 13, right? Anything else? Question? Tomorrow. And if we don't do it tomorrow, then we'll do it after break, but I'd rather do it tomorrow. That way you're not having to like stress about that the day after break. Okay? And you guys ready for 13? 13 is a weak acid problem. And what we're going to talk about is just baby basics of that, because I know that after break we'll have equilibrium, which is our final chapter, kind of our final like topic to talk about, and it's going to be very clear what I'm talking about then, so I'm just going to give you the brief of it. So weak bases or weak acids, either one, let's just do weak acids, so I think that's how it was phrased in your question, don't 100% ionize. True statement, right? You know that. And so I sent out a quick video on how does this look, but it's really indicative of, can you write a reaction that looks like it doesn't 100% ionize? Yes, you can. Anytime you write HA, that's like our generic form for an acid, and you add it to water, generally acids make hydronium in water. That's the definition of an acid, according to Arrhenius. And so if the acid gives its H to water, what's left over? A loses an H+, so it becomes more negative, right? So that's going to be an A- charge. Well, this shows 100% forward reaction happening, but that's not true because we don't 100% ionize, or we don't 100% make ions. So this is a reversible reaction, so that means it can go backwards, which means which actually it does quite a bit. Most acids are usually like 98% present over here, meaning like didn't dissociate, didn't ionize, and only 2% or so are going to ionize. Well, we can assign a mathematical way to solve for this value, and it's called making an icebox, where you plug in your initial concentration here into the row here. You plug in the change that's occurring here, and that's true for each of these individual reactants and products. And then what you do is you describe the concentrations at equilibrium, and then from there, if you can find the concentration at equilibrium of this guy, because really no one cares about the acid at the end, no one cares about the water at the end, no one cares about this little anion that was made at the end. We only care about the concentration of hydronium at the end, because what do you do with that to find the pH? If you have the concentration of hydronium, how do you find the pH? Negative log, right? So this is, I'm not going to show a complete problem with this because it's above our pay grade right now. We don't need that at this very point in time, but there is a more complex method of finding the pH of weak acids and weak bases that are more than just take your concentration, plug it in. You actually have to do take the journey to find its concentration and then plug it in. But that's called an icebox, and that's what you would do for anything weak, but we will do that after break. Okay? Any other questions on part 19? The only thing I did know, someone asked a couple questions on the true-false section, and I thought it would behoove you to have those answers for yourself. So, if I find where I put that. Here we go. 1, sometimes true. Thumbs up if you got that right. Thumbs up if you got it right. Thumbs down if you didn't. Maybe kind of give me a full, complete survey. Number 2, not true. Okay. Not true, number 3. All right, I might have to go over that one in a second. Oh, that was the one about basic nomenclature, right? So, like, was there a special system for naming bases? Was that question? Yeah, there's not a special system. It's just like, hey guys, hydroxide. That's it. It's just a normal polyatomic we say. Acids are like, whoa, if it's binary, you say this. If it's ternary, you say this. It's got like a more involved system. 4, always true. 5, always true. 6, always true. 7, I don't know what it said. I think it said not true and according how it was stated. Oh, let me pull that because I told someone else this yesterday. 7, if it's less than 10 to the negative 7th, then it's a basic solution. So that's not true the way it was written. But you should know that we kind of just talked about the exponents give you indication if it's acidic, basic, or neutral. 8, not true. 9, not true. 10, always true. 11, sometimes true. 12, sometimes true. 13, sometimes true. 14, never true. And 15, sometimes true. And give me a 10 out of 10 if you got at least 10 of those right. At least 10 of those. Which one is that? Number 10. Ammonium ion is a Bronsted-Lowry base. Oh, it's a Bronsted-Lowry acid because it always donates. That's actually not true. Bronsted-Lowry. That's supposed to be not true. My bad, guys. And occasionally, like, this is an old answer key from my first run of having this problem set. So it may be that I have a different problem set than you guys at this point. I've tried to update, but I don't always rescan. Okay, so let's pause on that for a moment. Get on your computer, open up Chrome. We need to do a tutorial real quick. And the tutorial is something you've probably done in another class, but you have to do it with me as well. Everybody's got to do it. So when you open up Chrome, don't open up to your calendar like I did, and click on the apps little box over here. Do you guys know what I'm going to do? Yes, you've done this 100 times, but you have to do it in every class. So give me a thumbs up when you click the apps icon, which is the upper left-hand corner. When you click this, it'll come up with a number of apps that are available to you. We're going to click on the NC Test icon. Once you click on the NC Test icon, it'll come up and it'll kind of take over your computer. That's why I say grab your computer so you came in. If you don't have, sorry about that, if you don't have a school computer in front of you, you need to go ahead and get that for yourself now. And we're going to continue. You guys are going to do the test tutorial, which is in the lower right-hand corner. And you're going to select, give me a thumbs up if you're here. Thank you. You're going to select a test type. Let's do NCFE Science since you're in a science class. In the science tutorial, you can change the a couple settings. None of you will do read aloud. None of you will likely do large font unless you don't want to see the question on one screen. You just do a lot of scrolling, but you do have some options there. I'm going to choose gray. I'm going gray. You guys can choose whatever color you want. You hit login. Who's seen a test like this before in their education life? You've seen these tests before. There are many times that you'll have your name, your student ID, and then your school will appear there along with the test. Your teacher on exam day whoever's administering your test will go, you may begin. You click start. So I want you guys to go ahead and play with some of the tools. I'll demonstrate them up here, but if you're ready, you can continue. I have to make sure I'm reading my script 100%. Don't close it yet, guys. Do not close it. Don't close it, guys. This is like, you know, I get paid for this. Make sure that you've done this in the tutorial. Alright, so some of the tools you would have seen are the flag tool. So just look up here if you're at the end of yours already. The flag tool makes you flag the question, and at the very end it'll say you flag these questions. That means that you probably questioned yourself and you need to go back to it. The X tool makes sure that you can cancel out answer choices to kind of give you a visual that you cancel those out, because you will have paper to write on. And chemistry, good lord, you better be writing on that paper, because there's there's some stoichiometry, other equations you'd be plugging into. You will write on paper. Okay, don't be that person that's like, I didn't write anything down. Please write something down for yourself, because you know that's how you practice. That's how you should also perform. Highlighter tool, if you're trying to make sure that you're seeing the keywords, you're like, oh no, I didn't want to highlight that. Scratch it back out. Xing out highlight gives everything, all the highlights away, and the question bar gives you like a tutorial on how to use the tools available to you here. And then at the end, once you proceed through the questions, you can go to the end and it gives you the recap of your assessment. It also tells you where you flagged the question so that you're like, oh, I forgot I didn't know number 1. Let me go back. And as you click on that again, it brings you back to the first question for you to have that second look or third look, whichever one you're doing. And everyone hit review now. Make sure at the end, once you hit at the end of the test, you're going to say, okay, I'm done. You hit end test. It's going to be like, are you sure? And you go, no, I'm not. Cancel. Or you're at the end of the test and you're like, yep, I'm done. I have answered the 40 questions proficiently, and it says you're done. Exit. And then you guys can exit that, and I'll tell you where we'll go shortly on the computers. You won't need the computers for about 30 minutes or so. So if you want to close them to save their battery, that might be a good option. Okay, look, done. All right, we're going to talk about titrations now. So you will need a calculator. You guys are in the middle still. You are going to need a calculator. Jacob will pass out calc. You know what, guys? The calculators, a couple of them are like floating around here fast. So Jacob will pass out. Finish that while we kind of get going here. So we're going to do about 3 or 4 examples of titration. Then we're going to work on a web quest that will simulate how titration is performed in the lab. Because tomorrow we're actually doing a titration. But the equipment is pretty pricey. It costs approximately $100 to $120 per lab setup. So I like to make sure we are absolutely wonderful at knowing how to set that, so that whenever we actually have to do it, we're proficient. So right now, go ahead and have a piece of paper out on the back of your lecture notes. Have your lecture notes out. Let me see them. Sorry, Emily, because hers is right here. So the lecture notes that we started with the crossword on them, flip it over, and you'll see titration notes. Now, these are mainly just the notes that have kind of a description of the process along with some lecture examples. And I'm going to, like I said, do about 3 or 4 of them. But once you get the hang of it, let me know, because I want to make sure that you have time to practice by yourself in class as well. Because right now it's already 8 o'clock, and so I want to make sure that you have the time you need to ask me questions. You guys ready? Okay, I am taking problem set 19A as well as your lab, so just kind of hold those to the side. That way you know that those are going to be turned into me. Okay, so what is starting to happen here is this is an example of a burette. This is a long skinny tube. This is what's this one called? Flask. Yeah, that's a flask. What we have in the top of here is we have a solution. Usually it's sodium hydroxide or a base. And down here we have an acid. What is an acid-base reaction called again? It has a name. There's only 2 types of reactions in this whole unit. Neutralization reaction. Okay, so this is a neutralization reaction. The titration, which it doesn't say up here, okay, the whole process is called a titration. The titration is a volumetric analysis, so volume meaning we're looking at volumes and analyzing the volumes to determine the molarity of a particular substance, either the base or the acid. So, as you can see, the base is being added to the acid. What color is the acid right now? Clear, okay? Phenolphthalein is in there. Phenolphthalein is an indicator, indicating to us that the titration is moving along, and at some point we're going to meet something called the end point. So looking down here, you see that with your flask, you see a little tiny dot of pink. That means that the indicator is starting to want to change pink. That means for this particular instance, because phenolphthalein, it changes at pH approximately 8. That's when it's going to go from clear to pink. And you have to know that pH. You have to know when it changes colors. Litmus paper, you have to know the color changes, and phenolphthalein. The other ones, there's a lot of other indicators out there, but we really definitely need to know phenolphthalein. So what pH would you assume that we're getting close to right here? because we're adding base, right? So we're starting out acidic, let's say pH of 2. We're adding base, we're adding base, we're adding base. So what's happening to our pH? So it's increasing, it's getting more basic, okay? What do you think is happening? What pH are we approximately at right here? If we know that it's going to change at 8. Maybe 7 or 7.5, something like that. Okay, you wouldn't know that, but the indicator is telling you that. And then you see that we're like that light pink, that's really good. That's probably right at pH of 8 or so. And then if you're that person like, I think I can get one more drop in there. Well, indication is going to, the indicator is going to change color dramatically once you overshoot its endpoint, which is the pH of 8 here. So we're probably at like pH 9, and that's like a really dark pink. We don't want something like that when we do our lab tomorrow. That's called overshooting, so that's too far. But the point where the pH changes just perfectly, just a hint of the color that it should be, we call the endpoint. That is not the same thing as an equivalence point, but we're going to make a distinction between the two shortly. So a pH curve, which you're going to see next, comes in many varieties, but the one that we'll mainly focus on is strong, strong. So this is an example of what you would, if you had a pH probe to track every single dot, every single volume added to see the pH, you would get something like this. But what we're looking for is my initial, and using phenolphthalein, you can definitely tell this, is my initial solution clear? Yes, it is acidic, so we're starting off really low on the pH part of the axes here. And this is volume of base added down here. So, and it makes sense as I add base, what's happening to the pH? It's going up, up, up. But then we have this exponential increase, right? This exponential increase is because the pH of something is based on a base 10 scale, right? So a pH of 1 is how many times different than a pH of, like, let's do pH of 3. pH 1 versus pH 3. Is it 3 times different? 1 times different? It's actually 1,000 times different. So base 10, it means 10 to the first is what this basically is referring to, and this is 10 to the third, which is what that's referring to. So this is 10, so that would be 100 times different. So this is base 10, this is base 1,000, right? So we have 1,000 or 100 difference between them. That's why the pH jumps so quickly, because it's exponentially based, not like linear based in terms of your math. Okay, so at pH 7, that's what we call the equivalence point. And the point that's true, and there's a little sketch that you can graph on, or there's a graph on your paper, you can sketch this graph for yourself. This is going to be the graph that we mainly focus on. There's other variations of this, but this is a good one to know. And you will see a pH curve on your test, and you all have to sketch one for me as well. So volume added is on the very bottom, so that's our x-axis, and then the y-axis is pH. And you'll know that this one happens to be at pH 7. That's called the equivalent point. So what does it sound like if you hear the word equivalence? What are you assuming is there? Something is equal, right? I heard someone said equal. Okay, so that means something is equal. And I'll tell you, it's the moles of H plus equals the moles of OH minus. And that makes sense because we have, actually, in this case, a pH neutral, pH 7, moles of H plus equal moles of OH minus here. It doesn't mean their concentrations necessarily are exactly the same. Depends on our volumes added. And then, like I said, phenolphthalein changes at pH, starts to change at pH 8, 8.5 or so. Another one that we likely will not use today or tomorrow is methyl red. It changes really low. What we want is we want our endpoint to be approximately the same as our equivalence point. Well, the endpoint, tell me what the definition of endpoint is again. Say again? Okay, so when the indicator that perfect amount's been added where the indicator starts to change color. Okay, so the endpoint for us is right here. Use a different color. The endpoint is about right here, so about, actually it looks like 9 on this graph here, and that's when phenolphthalein changes color. But you can see it's very close to the equivalence point, which is good for us because I can't see this happening during the titration, but I can see the color change, which is what we depend on. Indicators indicate to us where the pH is changing at the point where the indicator changes color. So I'll have some more information with this. But let's go ahead and just look at the other curves that are available. I'll come back to this particular graph. So for the graph that you guys just did, that was a combination of sodium hydroxide and HCl. HCl and sodium hydroxide. Strong acid, strong base, right? Strong, strong. Strong acid, strong base. They ended at, or their equivalence point was at pH neutral, pH 7, which made sense because strong, strong, neither wins. They have to meet in the middle at 7. But then look at something like this. Let's go with this blue graph right here. I'm telling you this is a weak acid. What's the first thing you notice that's different than the red graph with that blue graph? It starts higher. Doesn't that make sense for a weak acid? It's not as strong, so its pH starts a little higher, not quite at 1, but more like 3 or 4. So that's the first point that you see is different. What's another point you see that's different? Where is its equivalence point? Say again? So let me give you a little bit more information on the equivalence point, and then I'll ask that one more time. The equivalence point is on the vertical section, halfway up. So the first equivalence point is this red one. Let's say the vertical section starts about there, ends about there. What's about in the middle? Hopefully 7, right? Okay, so that's about 7 right there. And that's where the strong, strong combines to have its equivalence point. Now this is a weak acid and then a strong base, because I can see the strong base is still ending up where the 14-ish is. So what's halfway on the blue section? About 9, maybe close to 10 even. So I would say it starts getting pretty vertical about there to there. So halfway up is about here. It's about 9, close to 10. And so what you should see is that pH more acidic or more basic? More basic. Why does that make sense? Because what are we combining here? Right, a strong base and a weak acid. Strong bases win, pulls the equivalence point towards itself. And then vice versa, we could see the same thing, but with a, I don't have that graph on here. Well, kind of I do. Okay, so this one's a backwards one. I'm starting with an acid or base with this titration. Base can start at pH pretty high, and slowly it goes down to a pH of something more acidic. But at this point, let's go with, I'll go with this pink one for now. I'm going to kind of highlight it red. Okay, where is the equivalence point on the pink one? pH what? 5-ish. Okay, so the vertical section's there. About halfway down, it's probably about here. Yeah, probably about 5, 5.5. So, based on where the equivalence point is, what is combining to make this graph happen, to make this reaction? Strong acid and a weak base. Because that's the only way you're going to pull the pH down to the acidic realm, which is to have a stronger acid than a base. So there's our titration graphs, and those graphs are they help understand the reaction that's there. But right now we're more important with the calculations associated with these. These are just visuals to give you some pieces of information that might be helpful. Can I move on? We're going to do reactions with calculations with these. Okay, so we kind of talked about that. There's a couple. I have a bunch of these graphs. I'm going to go past these. We'll go back to the graphs later. Okay, so first off the bat, raise your hand if you can tell me the difference between equivalence and endpoint one more time. This is a big piece of information that's just I'm going to hammer with you guys. Equivalence point, what's true? Shout it out. You should have just written this down. Thanks, Cameron. Great, so the moles, and I'm going to call this moles of acid equal moles of base. Oops, moles of hydroxide are base, okay? Okay, so, and let's go someone from this table, tell me what the end point is. I would love some participation in lecture to give me some feedback, because that way we get to your homework as much as we can. Lindsay? Can you say endpoint? Endpoint, yes. Endpoint.
Oh, I think it's but just like the right pH.
But what's happening at that pH? Thank you. So this is when the indicator changes color. And so it's got to be at a perfect pH to do that. And we want these two pHs to be very close to each other so we know that our reaction's occurring correctly. And then last reminder, what is molarity? Once again, units for molarity. Shout it out. Moles of solute, and I'm going to say moles of acid, or moles of base in this case, because it depends. We're talking about acids and bases truly, mostly right now, over liters of solution. Okay. Pull my stuff down. All right, so what we're going to start off first is writing reactions, and then with that reaction, we're going to talk about the math behind it. So this is on your paper. Let me come back to this as we go. I'm going to do that with an example, but here are your 3 steps. These are your 3 steps for how do you start a titration example. The titration examples will always, always, always be a neutralization reaction. And again, what's neutralization reactions combine? Acids plus bases make salts and water, right? And you wrote that down yesterday on your notes. Okay, so that's our first step. So let's go ahead and do that. A student titrates 20 milliliters of a sample of a solution of hydrobromic acid. The titration requires 20.05 milliliters of a 0.1819 molar sodium hydroxide solution. What is the molarity of the HBr? So you just heard a lot of numbers. You heard that there's a reaction happening. What is the reaction? Shout it out. Let's go. HBr. Okay, you see one of the reactants is HBr. Write this down with me. I should see everybody having a couple of sample examples. That way you have some support. Darcy, what's the other reactant? Sodium hydroxide, that's Na. Hydroxide is just OH. Okay, we want to say hydroxide is HO, but we can't write that. We write it. Okay, so that's hydroxide. Double replacement reaction. Margaret, tell me one of the products. Okay, so she's combining the H here and the OH to give HOH. And then, Ayana, tell me the other product. Good, so this is the plus and this is the minus. We have to combine them in that order. Sodium bromide. And who's the salt here? Sodium bromide. Good. And that's balanced. We're good to go. All right, so that's the first step. Second step is to identify the titrant and the analyte. Let me explain what these are. In a titration, okay, we have 2 names. Actually, more like 4 names. We like to call things the same thing as many ways as we can. So I'm going to scroll back for that real fast. I just need a little bit more space. Well, I don't have any space there either. All right, so in your burette, it has volumes on it, and then your flask. We don't really measure much in the flask, but what we do is we'll put the acid in the flask. This has an unknown, and you might want to sketch this out for yourself. This has an unknown concentration. So an unknown molarity. This says volume, by the way. It looks like that. This big piece of glass, which you'll use tomorrow, is called a burette. B-U-R-E-T, burette. And it's pricey, which is why I want to make sure we know what we're doing tomorrow. It's like $100, and it has 2 pieces to it. The glass section, and then this section down here, it has like a little knob on it that you can turn. This is called the stopcock. Okay, you flip it, it lets liquid through. You flip it back, it doesn't let liquid through. So it opens and closes as you go. And so what we'll do is we'll slowly add. If I have acid down here, what do you think's up here in the burette? Base. Okay, slowly add base of known concentration. And as we slowly add that concentrated, whatever solution we have of our base, we're going to slowly increase the pH, and at some point we will get to the end point. But these things have different names. It's just how, like, common knowledge that we kind of talk about them so everyone understands what we're talking about. If I'm talking about the thing that's in the burette, which in this case is a base of known concentration, this has 2 names. This can be called the known, like, because it's known, it's pH, or it's called the titrant, because it's what you're titrating. It's the process of titrating. It's called the titrant. the flask down here, which contains the acid, has the unknown concentration. Well, we call that the unknown. You're like, that's really creative. Or it's called the analyte. And that's, analyte sounds like analysis, analyze, that's what we're analyzing. We're trying to find its pH. We're trying to find its concentration. We're analyzing the situation to find its concentration. So known or titrant versus unknown or analyte. All right, so now let's go back here. Going back to that question. In this question, who is the thing we know everything about? Meaning volume and molarity. Say again? Right, we know everything about it. We know the titrant, which is the known, is sodium hydroxide because we know both the volume and the molarity for it. We're analyzing information about the molarity of HBr, so that must be the analyte. Okay? And so then I'm telling you, begin the stoichiometry, which is the process of canceling units with math, with the titrant. So here's me modeling that for you, okay? So I know everything about this. I know molarity has moles per liter. I know I can't cancel liters right now because what volume do I have? Milliliters. Take that 20.5 milliliters to liters for me. How do I do that? Okay, so I see people moving the decimal back. Can I just do that, or do I need to show the process of multiplying by dividing by 1,000? Can I just bounce that decimal back? How many places? How many places? 3. What's that volume? 0.02005 liters. Okay. And I'm going to take those liters, I'm going to multiply them by my molarity of my solution. So multiply by 0.1819. Molarity is moles per liter. And this is like liters of solution. This is the solution that we're speaking of over here. But who is this describing? Moles of what? Who is this referring to? Sodium hydroxide, right, NaOH. Because now it's important for us to recognize I have a lot of information with the base. I don't have much information about the acid, but I do know how they interact with each other. They react in a 1-to-1 mole ratio. I'm back to mole ratios. If I have a reaction and I have math associated with it, I'm usually using that reaction for its mole ratio. What's the mole ratio between them? 1-to-1. Who do I write on bottom? Thank you. 1 mole of sodium hydroxide on top. Who do I care about? I don't care about sodium hydroxide. Who am I trying to get to? HBr, right? 1 mole of HBr, and these are just from the balanced chemical equation. So I'm now to the point where I'm kind of like, all right, guys, I'm really close to the concentration of HBr. Right now, I'm just at moles of HBr. If I want to get to concentration, aka molarity, what do I need to do with that mole? How do I get from moles to molarity? Divide by volume, right? So I'm actually going to stop here. Let's get moles, and then we'll secondarily divide by volume. Calculate for me. Because I know this is how some of you guys will want to solve it, and I'll do it a second way shortly. So what's 0.02005 times 0.1819? 0.00 what? Can I get one more sig fig?
4.
Thanks. Can I get a second on that? 4 or 5? Okay, it's cool. It's cool. So this is HBr, right? Okay, so I've got my moles of HBr. What's my volume of HBr I have in the problem? 20 milliliters. Well, 20 milliliters ain't going to work for me, right? I need that in liters. How many liters is that? Okay, so take your moles divided by your liters, 0.02000 liters, and what is that? When you divide. Shout it out for me. Say again? 0.1823 molar HBr. Because once we've gotten moles per liter, that gives us the chance to kind of change our units back to molarity, which is what moles per liter is. And that is 0.1823. Let's think about if that makes sense as we go here. So first we reckon the reaction, because reaction is required. We have to know how they're comparing to each other, meaning their mole ratio. We took the information that went together, which was the volume of the titrant and the molarity of the titrant. Basically, we did this because what do we want to cancel out? What unit did we cancel? Say again? Thank you, EJ. Liters and liters canceled, because we don't care about the liters actually at this point. We want to get to moles of sodium hydroxide so we could secondarily get to moles of the other guy, the acid, which we did in a mole-to-mole ratio. So moles of NaOH canceled. Then we got some moles of HBr. We're like, yeah, we're almost to molarity. Take your moles, divide by your liters, you get to molarity. Basically, didn't I use almost exactly the same volume for both of these? 20.05 and 20. Well, if I use almost exactly the same liters, and I use, it's a 1-to-1 ratio, I should probably have really close molarities because everything's pretty equivalent. Don't I have really close molarities? 0.1823 versus 0.1819. Yeah, that all should make sense because they're just reacting in a 1-to-1 ratio. Another one. This one is for you. Now, I will tell you vinegar is, it says right here, vinegar is acetic acid. Follow your steps. I'll come around and help. So as up here real fast, I know you might be in the middle. I just want to help you with organizing your information one more time. And so after this, continue. But some people get lost in finding the numbers in the question, so why not just pull them down as normal? You normally write your givens down in most of these. So as you're organizing, you should see that the question gives me volume of the acetic acid, but not the molarity. And it gives me the volume and the molarity for the sodium hydroxide. Who's the titrant? Sodium hydroxide, it's the known, right? So it's the thing I'm titrating with. Who am I analyzing? Who's my analyte? Gotta be the other one, right? And that tells me that I must start my process with this, because that's the one I know everything about. So continue. guys up here. So in terms of what you achieved, you'd likely put your volume and your molarity next to each other. You multiplied and canceled your liters. You got 2 moles of sodium hydroxide. Check. Thumbs up. Okay. Then you took your mole-mole ratio and went to acetic acid by using the Bounce chemical equation because it was a 1-to-1. You would likely stop here, got moles, and then separately divided by volume. But isn't dividing the same thing as multiplying by the reciprocal? Yeah, so that's what I'm just showing that here one more time. This is another way if you don't want to stop in the middle and you want to just continue your calculations. By multiplying them by the reciprocal, you take 1 over the volume, so 0.015, and you will get the same results, right? So moles of NaOH cancel. Lastly, we have moles of acetic acid over the liters, so that gives me molarity, because those are the two units that didn't cancel. That gives me molarity. What's your answer? 0.832 of acetic acid. Very good, guys. Let's do one more, but I'm going to mix it up and actually answer one that doesn't solve for molarity. It's going to solve for something else. So give me a second and I'll get there. I just want to make sure we have some people able to get down what they need to. Can I proceed? Yes or no? Yes? Okay. This one's interesting because at the end it asks us to solve for the pH. So I can either do this one or I can do one of the ones that are on your lecture ones, which are, it says practice UCIC practice 1 through 4 or 1 through 3? 1 through 3. How about you guys look at those and you tell me which one you want me to do? Either the one I just showed, the strontium hydroxide one, or one of these. Just put them in the air, 1, 2, or 3. I only have a couple people in my survey. I see a mixture of 2 and 3, so I'll help set up both. But let me start with 2. Okay. Well, let's just talk about 2. After you set up your Bounce chemical equation, who are you going to start with your process of stoichiometry? HCl, because this is your standard, this is your known. Once you get to multiply those, you get to moles of HCl. What would you have to do next? Once you get to moles of the standard, you'd have to get to moles of the other guy, right? So the base in this case. Okay, so we get to moles of base. If I'm at moles of base and it says what's the volume, what you'll notice is you haven't used this yet, right? But this is 0.12 moles per liter. Who says you have to leave it like that? Can't you flip a conversion factor? If you flip this conversion factor, it gets liters on top, which is what you want. Okay, so 2 I think you can achieve if you remember you can flip conversion factors. I'm going to leave that one to you. I thought number 3 was the harder one, so I'm going to go with number 3. So let's work through this one together. Write your reaction first. Go ahead and do that. What's the formula for aluminum hydroxide? Okay, put them in the air. What's the charge of aluminum? You should be able to look at your periodic table. If you're in a 3rd group, it loses 3 valence electrons. It has a 3+ charge. As it combines with hydroxide, it drops that 3 down as well. And then hydrochloric acid we've written about 1,000,000 times. Go ahead. And what's the products here? Nick, tell me one product.
Yeah, I'll see it.
Good, because you crisscross your charges. Very good. Kyle, tell me the other product. HOH, and then balance it, everybody.
3 in front of the water.
3 in front of water and HCl. Good. Okay, so we now see this a 1 to 3 ratio, right? That's pretty glaringly obvious. Then we see that we have 55 milligrams of aluminum hydroxide, and then we have 0.2 molar HCl. And it says how many milliliters of the acid is needed to neutralize the aluminum hydroxide. We haven't started like this yet, right? Which one are we analyzing? The acid or the base? We're analyzing the base. So can we start with the base? Yay or nay? No, the one I'm analyzing, the one I'm looking at for the question, it has to be the very, very end. So I have to start with this one, right? Well, we just simply haven't started with milligrams, but who says we can't get milligrams to moles, right? We can do that. So get my milligrams. Oops. The smart board and I are fighting today. Sorry, guys. Okay. So take my milligrams of aluminum hydroxide and get me to a reasonable unit. What would be reasonable to come next? Grams, right? I can't do much with milligrams, so I can go to grams. Okay, so what do I write on top? Who gets 1,000, the gram or the milligram? The milligram. So milligram gets 1,000. There's 1,000 milligrams in 1 gram, and that's still of aluminum hydroxide. Okay, now I'm in grams, right? So I need to get from grams to moles, likely. Okay, so get me from grams to moles. How do I do that? I should see you ripping out your periodic table, whipping it out, calculator. If there's a periodic table nearby, maybe you could glance at that. Jacob, periodic table.
77.98.
Let me just verify that in my head real fast. 17 times 3 is 41. 41 plus 27 sounds about right. What is it?
77.98.
77. I'm just going to round to 78 because it sounds wonderful. I am assuming that different periodic tables have a slight difference there. Okay, so 1 mole is equal to 78 grams of aluminum hydroxide. Okay, so far milligrams have canceled, grams have canceled. I'm in moles of aluminum hydroxide. Nobody cares about the base. We care about the acid. Get me to the acid. What would be next if I'm going from moles of base to moles of acid? Mole ratio, right? You can't just go from moles to moles without using your mole ratio. That's a 1 to 3 ratio. Who goes on top? 3 moles of who? You guys are so chatty today. HCl, thank you. And then what goes on bottom? 1 mole of aluminum hydroxide. So that cancels our aluminum hydroxide out. And the final step, I'm going to kind of scooch down here. So what you'll notice is that on top I have moles of HCl. The only thing I've yet to use is this right here, 0.200 molar. What's molar again? Okay, so that's moles of HCl over 1 liter of solution. If I took this and I plopped it down on my next step, what would cancel? If I left the moles here and I plopped this down, would anything cancel? No. What do I need to do with that? Flip it, right? So taking my molarity as a conversion factor, 1 liter goes on top, 0.200 moles of HCl go on the bottom. So that would cancel this mole of HCl and this mole of HCl. And I'm in liters, but the question wasn't liters, the question was milliliters. So my last step would be what on top? 1,000 milliliters is equal to 1 liter, and that liter here would cancel. Woo, doggies. Calculate. It's like 0.1 something, 0.12. What is it? Say again. Oh, sorry. I was trying to do math in my head. Oh, yeah. I moved this one around. Okay. Like twice. So 10 point what? Just gonna leave it like that. I know we could go sig figs, but that is for it for now. What is it? Do 5.8. Okay. All right, guys. I thought we would go to a simulation today, but I don't want to rush that. I will pop up tomorrow, and I'll likely move our lab to Today, after breaks, we'll start a lot when we jump back in on break day. But let's go ahead and switch modes. Let's go to problem set 18. 19B, sorry, 18, sorry. Problem set 19B, which you have on the paper with problem set 19A. So when I take problem set 19A, if I'm able to take everything, right, you should have your information likely on a separate sheet of paper. The math anyway. So two things I'm looking for, okay? Thank you, Jillian. Move my for me. So what I want you to do is finish. This is homework, okay? Then you guys have about almost 10 minutes or so right now. Finish lectured problems. That's the one that I didn't do, plus the two that was on the student practice, the practice section. So there's 3 questions there overall. And then I'm going to say about 75% of PS 19B, because at this point you should have everything you need to do that. Really, truly everything. Tomorrow we'll do a simulation, and then we'll also do a sort of review with layout this time. Okay, so laptops can go up, and I want stuff that's yours. I want the 2 labs, and I want problem set 19A. So I'm going to pass around staplers for you to staple. Staple your problem set in your labs. Guys, please don't waste your time. You have stuff to do. Did you finish the lab? Guys, don't worry about turning in the strong or the strong. The sunrise never rain always. I was worried about you, so you need to keep it just nice and neat, not turning it to a thing to keep paper. Only turn in the problems nice and neat and class. So yes, laptops up and make sure that your stuff gets in the box. I was going to go take it up, but you guys have legs. That means get most of it done. There's 3 questions, yep. At the end of class.